Good morning, everyone. I am Ajit Suresh from IASC Bangalore, India. I am here to present our work on Oblivious Transfer extension titled Fast Actively Secure OT Extension for Short Secrets. So, this is a joint work with Arpita Patra and Pratik Sarkar of IASC. Before going into the presentation, let me give you a brief outline. I will start by introducing a fundamental primitive in multi-party computation named Oblivious Transfer, or in short OT. I will then move on to OT extension, which is a magical technique used to generate a lot of OTs starting from a small number of OTs in an efficient manner. Next, I will describe a protocol for OT extension in the semi-honest setting. So, by semi-honest, we means the corrupt parties follows the protocol correctly, but they are curious and they will try to obtain some additional information which they are not supposed to know. This protocol is by Kolesnikov et al. In 2013, and we will refer it to as KK13 protocol. I will conclude the presentation by presenting our work, which is the extension of KK13 protocol to the malicious setting. By malicious, we means the corrupt parties can arbitrarily deviate from the protocol. Let me introduce the Oblivious Transfer primitive first. Consider two parties, Alice and Bob, where Bob has two messages, x0 and x1, and Alice has a choice bit, sigma. Bob will input the two messages, the x0 and x1, as his input to the 1 out of 2 OT box, and Alice will use the sigma as the input to the box. At the end of the protocol, Alice will receive the message corresponding to her choice bit, that is x sigma. In normal message transfer schemes, the sender knows which message he transferred to the receiver. But here in OT, the sender does not know which message he has transferred, and thus the name Oblivious Transfer. So here, Bob does not know the value of sigma, and at the same time, Alice has absolutely no information about the other message of Bob, which she is not supposed to know. A generalization of this scheme is 1 out of n OT, where the sender has n messages instead of 2, and the receiver has a choice string instead of a bit. The importance of OT can be seen from the result of Killian in 1988, stating that OT is complete for MPC. This means OT is the only cryptographic primitive required for constructing any MPC protocol. There is a known result stating that OT cannot be based on symmetric key primitives alone. This means we need expensive public key operations for constructing OTs. For circuits, like when we are using MPC, for circuits like AES, we require millions of OTs. So here comes the idea of OT extension, where we start with a small number of OTs, which we call as base OTs, and generates large number of OTs. So as shown in figure, let's say we start with k OTs, and we generate poly k OTs as the end product. The advantage of this idea is that the conversion requires only cheap symmetric key operations. So in the amortized sense, the cost of one OT produced will be just the symmetric key operation. Moving to the protocol of KK13, consider the OT extension black box as shown. So here, the protocol generates m 1 out of n OTs starting from k 1 out of 2 base OTs. So here, the sender has m sets of n messages each, and the receiver has m choice strings, say R1, R2, etc. up to Rm. At the end of the protocol, the receiver will receive exactly one message from each 1 out of n OT corresponding to her choice and nothing else. Let's see the KK13 protocol in some more detail. So, I use the following notations in the presentation. For a matrix A subscript I denotes the ith row of the matrix, and A superscript j denotes the jth column. The KK13 protocol uses a linear code word named Varshadamat code word, or in short WH code word. So there are k Varshadamat code words of k bit length, and we denote C subscript I as the ith Varshadamat code word. So the distance between any two Varshadamat code words of k bit length is exactly k by 2. Now the first phase of the protocol is base OT phase, which is shown in this slide. Here the sender will act as the receiver and receiver will act as the sender. So the receiver for the base OTs constructs two matrices which are of dimension m by k, named T and D as follows. So the T matrix will be filled with random values, and the rows of D matrix will be filled with WH code words indexed by the choice string of the receiver. That is, the ith row of matrix D will be filled with CRI, where RI is the ith choice string of the receiver. From the sender side, sender will choose a k bit vector S at random. Now for the ith, consider the ith base OT. So the inputs from the receiver side are TI and TI XOR DI. This means TI is basically the ith column of matrix D, and TI XOR DI is the ith columns of matrices T and D XOR together. These are the two inputs from the receiver side, and sender will use the ith bit of vector S, say Si, as his choice bit. After the OT, the sender will receive the ith either of Ti or Ti XOR Di, depending on the value of Si. So he considers it as a ith column of a m by k matrix, say Q. So Qi denotes the ith column of a m by k matrix. They will engage in k such base OTs. So finally the sender receives the entire Q matrix. Okay, each column of Q matrix is either the column of T or the columns of T and D matrices XOR together. The rows of the matrices Q, T and D are related according to the relation Qi is equal to Ti XOR with CRI bitwise ANDed with S. So this means the row of matrix Q is equal to row of matrix T XORed with the bitwise AND of row of matrix D and the vector S. Now sender will use this Q matrix to construct the mask for his messages. Consider the ith one out of n OT. So the sender has n messages with him, say xi1 to xin. So the sender will use the ith row of Q matrix to construct the mask for these n messages as follows. So the first mask is of the form h of I Qi XOR with C1 bitwise ANDed with S. The second mask is of the form h of I Qi XOR with C2 bitwise ANDed with S, and so on up to n mask, where h is the random oracle. So using this mask, the sender generates n ciphertext corresponding to the n messages xi1 to xin as follows, and we call these ciphertexts as yi1 to yin. So these ciphertexts are sent to the receiver. Receiver will choose the ciphertext corresponding to his choice, say yiri, okay, and he decrypts as yiri XOR with h of iti, where h is the random oracle. So the correctness can be easily verified. Now the protocol of KK13 guarantees security against a malicious sender. So our task is to analyze the case of a malicious receiver. So consider the following strategy of adversary. The adversary is going to set the D matrix in the following way. The first row of this D matrix is filled with the first WH code word, except that its first bit is flipped. Now the second row is filled with the second WH code word with its second bit flipped, and so on up to k rows. Now consider the first mask in the first 1 out of n OT. It will be of the form H of 1 Q1 XOR with C1 bitwise ANDed with S. As I told you earlier, there is a relation between these rows of Q, T and D matrix as Qi is equal to Ti XOR Cri bitwise ANDed with S. So substituting the value of Qi in this relation, we get H of 1 T1 XOR with D1 XOR C1 bitwise ANDed with S. So here D1 denotes the first tweaked row of this D matrix. So when simplified, this will become H of 1 T1 XOR with a k bit vector, where the first bit is S1, which is the first bit of vector S, followed by all zeros. Now, given a prior knowledge about the underlying message X11, the adversary can find the value of this bit S1 with just 2 queries to Random Oracle. This he can actually extend for k 1 out of n OTs, and the entire bits of the vector S will be leaked, and thus the security is broken. Now, in order to formulate the problem, let's see the first mask in the first 1 out of n OT on the case where none of the rows are tweaked. So then the mask will be of the form H of 1 Q1 XOR with C1 bitwise ANDed with S. That is same as H of 1 T1 XOR with CR1 XOR C1 bitwise ANDed with S. Now, as I said earlier, the distance between any two WH code words is exactly k by 2. Thus, CR1 XOR C1 will preserve k by 2 bits, and when it is bitwise ANDed with S, the k by 2 bits of S are actually preserved, and thus follows the security. But the problem happens when the rows of this D matrix are tweaked. Like instead of CR1, some tweaked row D1 is used. So our goal is to ensure that the rows of D matrix are WH code words. So we achieve this by adding a consistency check in between the base OT phase and the sending masked inputs phase. So our check adds a communication overhead of order of mu into log k bits, where mu is the statistical security parameter and k is the computational security parameter. Now, moving on to implementation results, our protocol produces 1 out of n OTs. Since no efficient conversion from 1 out of n OTs to 1 out of 2 OTs are known in the malicious setting, we compare with the existing protocols by converting them to 1 out of n OTs. As you can see from the graph, the protocol of KK13, when the output is set to 1 out of n OT, outperforms all the existing protocols IKNP, ALSZ and NNOB. Here, IKNP and KK13 are protocols in the semi-honest setting, while ALSZ and NNOB are maliciously secure. When we compare our protocol with the protocol of KK13, which is secure in the semi-honest setting, our protocol improves the security to malicious setting by adding just a communication complexity of 0.028% overhead and the runtime of 3 to 6% overhead in both LAN and WAN settings. So with this, I conclude my presentation. Thank you. Any questions?